Hello, and welcome to the webinar titled Algorithmic Trading with MATLAB Products. My name is Stuart Cazzola, and I'm the Product Manager in our Finance area here at the MathWorks. Now before I begin with today's discussion, I'd like to take care of a few logistical issues. If you have any technical difficulties during the presentation, please use the Chat tab to correspond with the webinar host. And if you have any questions about the content during the course of this webinar, please post them to the Q&A tab, and I'll do my best to answer them all at the end of the presentation. So here's the agenda for today. I'll first start off by introducing the challenges encountered when developing trading strategies. I'll then give a brief overview of an algorithmic trading workflow and discuss our products and how they map into that workflow. Then I'll jump into MATLAB and start building a trading strategy, and in this particular demonstration I'll be using technical analysis and an evolutionary learning approach. And then I'll summarize our product solutions for high-frequency trading, as well as discuss a variety of the product capabilities that I didn't have the opportunity to demonstrate. Before we start building the example, I'd like to think about what are the challenges you face when building an application. So one of the first challenges is the inability to customize your models. So most commercial off-the-shelf software solutions provide a black box. That is, it does not give you any transparency or flexibility into customization. Now this can also be a challenge when presented with regulatory requirements, where you need to have transparent models. Another challenge is long development times. This is often the case when you're using a low-level language like C or C++, and it can take months to develop a model, going through the iterative process of writing to code, building it, verifying and testing it, and then doing that iteration over and over. And of course, there's the inability to handle complex and numeric-intensive algorithms. This is something many of our customers were previously running into with spreadsheet-type applications before they switched to MATLAB. And unlike Excel or Visual Basic for applications, MATLAB gives you the ability to handle large and complex challenging problems. And of course, there's always the time and cost of developing and deploying our applications. So let's start by defining the algorithmic trading workflow. The first step, of course, is to gather or access the data you need. This can be from a variety of sources, such as an Excel spreadsheet, a database, a historical or real-time market data feed. The next step is to research a trading approach and to quantify how well the approach will work. This includes data analysis and charting, developing custom algorithms, and backtesting them, and then putting all the pieces together to identify the best strategy or approach to use. Once you've identified a good strategy, or multiple strategies, you'd want to implement them. And in many cases, this means that you need to share them with others. This may be in the form of a report aligning the strategy or algorithms or the performance of your benchmarks, or it may be an application, be it a standalone application, part of another application, or even delivering a callable library or a component for another programming language. And it may also be C code itself, depending upon your specific needs. And of course, this process is iterative, and we may continually be refining our trading strategy and going through this entire workflow repeatedly. MATLAB Products provides a solution to span this workflow. And throughout the rest of this presentation, I'll be showing you examples of our products through both a live demonstration and slides that are covering different aspects of this workflow. So let's start with a demonstration. The best way to learn about MATLAB's capability is to see it in action. Now in this demonstration, I'll be beginning with an introduction to MATLAB and then build out a couple of different trading strategies using technical analysis. The goal is to develop an automated trading system, and the specific example I'll show uses the futures market. Now the techniques I'll be showing you are not limited to the futures market, and hopefully as we go through the demonstration, you can see how they apply to your area of work. So we'll conclude the demo using a genetic programming approach, or an evolutionary learning, to identify the best trading strategy from a variety of different market signals. Now the example we're using today uses technical analysis to generate the signals, but keep in mind that this approach can be applied to a variety of different market signals that you may get. For example, it could be indicators from sentiment analysis, fundamental analysis, portfolio theory, just to name a few. So even if you don't do technical analysis, you should find the evolutionary learning approach to be interesting and hopefully useful for identifying different trading strategies that you may want to implement. Okay, so let's get started. I'll go switch over to MATLAB and start the demonstration. Right, what you're looking at here is the MATLAB desktop. So for those of you who are new to MATLAB, I'll be giving you a brief introduction as we walk through the first step, which is accessing data and bringing it into MATLAB. So what we can see here is there's the current folder browser right here, which shows me the current directory I'm working in. So you can see there's an Excel file called bun_daily. So let's go ahead and open this outside MATLAB to get a view of what our data looks like. So what this is the bund future prices given a date in date number format, the open price, the high, the low, and the close. So what we're going to do is bring this data into MATLAB and to begin to explore it and start developing a solution around it. So let's go ahead and double click on it. This is going to bring up the import wizard, which allows us to import the data directly from an Excel spreadsheet. You can see that here's the numeric data, the text data that's contained in the spreadsheet, and which ones are columns header if they happen to be there. So we're going to go ahead and click this Generate MATLAB because I'm going to show you how easy it is to start learning MATLAB code as you walk through the interactive data exploration capabilities of MATLAB. So go ahead and click Next. So now I could bring in the data in terms of column headers, data, and text header, or I can use this create variables from each column using column names, which will go ahead and bring it in using the column name found in the Excel spreadsheet. So as you can see, here's the variables that are available now to me from that spreadsheet. And just to verify, we'll go ahead and open up Close and take a look at it in the variable editor. And you can see this looks like the numbers that were in the Excel spreadsheet. So things look like they imported okay. The other thing you see here is the automatically generated MATLAB file. It's named import file and is currently not saved. But what this is this is essentially the same commands that were used to bring in the data that was done through the import wizard. So if I have similar types of data, I can import that specific data once, create a function here that will allow me to re-import that data as many times as I wish. So let's go ahead and save this. We'll save it as import file. And let's go ahead and clear up or clean up the workspace. So now what you're looking at is the command window, and this is the area where you can enter commands for MATLAB. So let's go ahead and bring in the bun data as we did before using the import file function. So now you can see how easy it is to reuse activities that I've done before. So this is a key principle behind MATLAB, is we try to make it as easy and straightforward as possible. And everything that you do through the interactive point and click tools has an equivalent command that you can use from the command window, or you can generate code for certain actions you do, and I'll be showing a little bit more of that later as well. So what you can see is we have data. So let's go ahead and plot the close price. We'll just go ahead and click the drop-down menu here, and you can see a time series plot of the price where the x-axis is the frequency, which happens to be daily right now, and the y-axis happens to be the current price. Now also notice that as I created my plot, the command used to create the same plot is echoed to the command window. So another thing I can do is go ahead and add more data to this plot if I wish to, or format this plot to show exactly what I want to. So we'll go ahead and open Plot Tools. I'll click on the axis and say let's go ahead and add an axis label, which is the daily sample, the y-axis, which is the price, and we'll go ahead and give it a title. So this one we'll call Bund Closing Price. Now the other thing I can do while I'm in here is go ahead and format and add other variables to this as well. So for instance, I can decide to make this have two axes. I can draw, let's say, the open, drag and drop that here, and plot the open on there as well. But let's not do that. So let's go ahead and delete that data. And what I'm going to do is let's go back to the command line and define some more variables of interest. So one thing I'd like to do is to begin to develop a trading algorithm based upon technical analysis. So one of the first and straightforward ways to do that is to use a moving average. So there's a function called moving average that we can use to do this. You can see that this is provided in the financial toolbox called moving average, and here's a syntax that's used to call that. So I can have a leading and lagging moving average, as well as define my alpha, which is the control parameter for the type of moving averages, and define the assets. So if we look at this, let's go ahead and define my leading and lagging moving average. We'll define this on the close price, and let's just choose a moving average of, say, 5. 5 for the leading and 20 for the lagging, and we're going to use an exponential moving average. So now you can see I have two new variables, lead and lag here, that I can use. So let's go back to that plot I started customizing earlier. And let's go ahead and add the leading and lagging indicator onto the plot. We'll do this to both of these. So what I want to do now is actually add. So what we're going to do is actually calculate the return and put it on this plot. So let's go ahead and develop a trading signal and add this to the plot. So what I'm going to use for the trading signal is first we're going to define a variable called S, which is going to contain all zeros, the size of the button close. Trading, as close. And we'll go ahead and use this to define our trading signals. So the other thing I want to do is use the leading and lagging indicators to define when to buy or sell. So what we're going to do is when the leading indicator is less than or equal to the lag, we're going to have a short condition or a sell condition. Similarly, when the leading indicator is greater than the lagging indicator, or the leading moving average is greater than the lagging moving average, we're going to have a buy condition. So now I have another signal to use. So let's go ahead. Well, before I do that, let's go ahead and calculate my return, which is essentially just the signal times the difference in the closing price. And let's go ahead and calculate the cumulative return. So this will give me my cumulative return, the instantaneous return, and my trading signal. So let's go back and add these to my plot. So let's go ahead and add the signal and cumulative return. So what you can see here is the plot of the cumulative return giving a moving average trading signal. So this is an example of quickly using a technical analysis indicator to build up a trading signal. So once I'm done, let's say this is formatted the way I like it, one of the things I could do is go File, Generate Code. So this is going to generate the code that's used to recreate my figure. And this contains all the commands that are used to contain that specific plot type. Okay, so I showed how to basically start up and develop a simple indicator. So one of the things now I want to do is actually go in and add the command history window to here. So what you can see in the command history window is essentially listing all the commands that I've been typing during my session. So one thing that makes this nice is that I can quickly recapture work that I've done. So let's say I want to capture the development of the leading and lagging indicator. And we'll create a script. So it's going to copy these commands, and it's going to go ahead and open it up in the editor, which is, so you can see all the commands that I use to create the file. So let's also add the import file up here. Right, so what I have here is now is the making of a script that allows me to essentially capture or reuse my work. So one thing I can do is I can actually do load data. I can add my comments. And so forth. So I can go ahead and save this and start using that, but in the interest of time for this webinar, what I'm going to go ahead and do is open up a prepared script that I created earlier. So go ahead and close this, as well as this editor. And we'll go ahead and open up the script called Algorithmic Trading Demo 1. So this is essentially going to begin where we just left off with by interactively developing an algorithm from the command line or the interactive tools. So what I've done here is you can see that the cells that are denoted by the double % sign are highlighted by their own section, and they can be collapsed. Now these have special meaning, and later when I talk about generating a report for my script, these will have significance, and I'll talk about that later. But for now you can see I have some comments describing what I'm trying to do. This first section should look a lot like what we just did with the command line. We're going to load in data from Excel. This time I'm using the XLS read function directly. So what this is going to do is if I go ahead and clean up my workspace and execute this first cell, it's going to go ahead and load the data into a matrix called data. So we'll go ahead and open data. And what you can see is data has basically all the numeric data from the spreadsheet. Now the next thing I'm doing is I want to create a test set and a validation set to perform my analysis on. So I'll use part of the data. In this case, we're going to say 80% of the data is going to be used to develop my trading strategy. Then the remaining 20% is going to be used as my validation set. So what I'm doing is creating two bund close values. One denoted just as bund close, which is just the close value, which is the first 80% of the data. And then the second one is called bund close V, which is the validation data set. So this next cell is going to recreate the leading and lagging moving average indicator that we just used before. So let me go ahead and execute that cell, and you can see the plot, which I've now added a legend to it. Close, leading, and lagging. You can see it on the screen here. So this next cell basically does this, calculates the same thing we did before, the return, the trading signal from the moving average, as well as a Sharpe ratio. So one of the things is, so you can see here's the help file for the Sharpe ratio, which tells us essentially there's a function within the financial toolbox that allows it to calculate performance metrics. This one happens to be the Sharpe ratio, which is just the ratio of the average return to the standard deviation. Now one thing is that since we're dealing with daily data and the Sharpe function returns the instantaneous Sharpe ratio, to get a better feel for an annualized Sharpe ratio, something that's done over, say, a full year, I need to scale that by the square root of 250, so 250 being the number of trading days per year that I'm assuming. You'll notice it takes in the return, in R, as well as this zero value. Now what the zero value is cash, so essentially you can offset it for another risk-free investment. So we'll go ahead and calculate those metrics, and then we'll go ahead and plot the results. And this time I've added a title showing you what the Sharpe ratio is, and the results, the position of my trade, the cumulative return, the price, the closing value, and the leading and lagging indicators. So one of the things you can see is that I could zoom in. Now I've linked these plots with the link axis command, and I can zoom in and interactively explore my data and zoom back out, so I can look at regions more closely and inspect what's going on. We started the process of developing a moving average indicator. And so what I want to do now is I just basically want to show that the results that I've done so far, which take a leading value and the number of periods for the leading indicator and the number of periods for the lagging indicator, and show that you can actually use this same functionality that we've just developed for a simple moving average. So I've encapsulated what we've done up here in a function called lead lag. So we're going to go ahead and execute this one, which is essentially just a leading indicator of 1 and a lagging indicator of 20. So what that means is that this is the same as the data for one of them, and this is the other one. So this is one way you can quickly create a simple moving average. So you only have one moving average in this case. And you can see the plot. The green and the blue overlap on each other. So in this case, I have one moving average. And this is one way you can reuse that moving average, or the leading lagging function I created, to do not only just a single moving average, but also two moving averages. And you can see, given that I provide a lead of 1 and a lag of 20, what the performance measure would have been on our test set. So now the next thing is that you notice that the performance wasn't all that great. The Sharpe ratio is pretty low. So one of the things we could do is do a parameter sweep across that data, or do a back test and see which parameter for, let's say, just the lagging indicator would be best. And that's what this function does here. So what I'm doing is essentially sweeping from 2 to 100 for a single moving average and calculating the Sharpe ratio, and then we'll show the results. And you can say that here are the results for the best parameter for one single moving average, which would happen to be a leading of 1, which I defined as 1, and a lag of 49. So this is the one that gives me the best results over the 100 points that I've searched over. Okay, so let's move back to the case where we want to develop the trading strategy based upon the leading and lagging indicator, both having values. So that's what this set of commands is going to do. So we're going to loop over both the leading and lagging indicator, and then we're going to plot the results. So let me go ahead and calculate this cell, and once that's done, we'll go ahead and generate the plot. So what we have here is a surface plot with a color bar showing the value of the Sharpe ratio for values of different inputs to my lead lag function. What you can see is how the performance or the Sharpe ratio varies as a function of the input, and anything above 1, or anything above 1, which is the red color here, has a good return. So we could choose any of these combinations around here to get a decent return. And you can see that the peak is around here, which happens to be, let's check. The peak is around 13 and a 7 value. So let's go ahead and plot only the best Sharpe ratio. So basically what we're doing is we're going to find the max location of the Sharpe ratio. And if you notice, Sharpe is a matrix. This first function is going to find the max by the column, and it's going to return the row that occurred. Second one is going to operate on the max we found and return the column. So we're going to find the row and column, or basically be able to extract the indicator. So let me go ahead and execute this cell. And what you can see plotted now in here is that the leading and lagging indicator of 3 and 23 are actually the best. The one I chose on the plot earlier isn't quite the best, but it was close. So these are the best conditions found. And you can see the return here is about 21. So this is absolute numbers here. So this 19.1% is calculated based upon this return over the initial investment, which would be around 111, 112. So now that we're talking about trading futures here, you don't necessarily have to trade with the full face value. Usually it's a margin and it's less than, the face amount, which would be maybe typically around 25 or 30%. So this return could actually be substantially larger, but for simplicity I'm just going to base it on the assumption that we invested at least the face value of the future at time 0. So that gives us a relative measure of return, which also be useful if we were actually trying to develop this on a stock or an equity. So now if you notice, all of that functionality was run on our test set. So let's go ahead and run this on our validation set and see how well it performed. And you can see I get about a 4.9% return with these values. You can see the trading history here, which doesn't start out too well and then slightly improves. Although let's see if we can improve upon this a little bit more. So the first step that we did before didn't include any trading costs. So what we're going to do now is actually include the cost of the bid and ask spread. So this would actually reflect the return we could actually get should we be actually investing within the bund using this technique. So in this case, we're going to rerun the parameter sweep, taking into account the cost, which is now an input into my function. And one thing you'll notice here is that I've defined a new function called lead lag function. So let me go ahead and open that and explain what we're doing. So it's doing some error handling and it's running on top. But the reason why I've defined this as a function is because I've also created another function called parameter sweep. Now what parameter sweep does is it uses that function that I've defined here and will run it over a range. So essentially what I've done is I've encapsulated the for loop within the parameter sweep. And it's going to rerun it multiple times. So let me go back to the lead lag function again real quick. And if you'll notice, it's going to pass in a vector of data. So one of the things we're doing is allowing to pass in a whole vector of the parameters. And it's going to run on each of them. And you can notice I have this function called par4. Now the thing about a par4, which is different from a regular for loop, is that this section of code can be run in parallel. And it's called a parallel for loop. And the reason I'm doing this is so that I can take advantage of parallel computing to speed the time it takes me to do my parameter sweep. So to recall, what I'm doing here is I'm defining a function handle, which is essentially taking the lead lag function, which is only going to have an input of x. So it's the only input, and these are passed in as constant. So let me give you an example. So let's go ahead and execute this section of code. And if you look at llfun, it's a function handle. So you can also see here it's a function handle in the variable editor. So what I can do here is I can pass in values of x. So let's do 5 and 10 as an example. And it's going to return the Sharpe ratio for that specific combination. And what this is allowing me to do is use the parameter sweep as a generic function that could be run on anything as long as I define it as a function that takes in one input, a vector x, and this range. So it's going to pass the range into x and evaluate that multiple times. So let's go ahead and execute this cell. But before I do that, what I want to do is I want to actually open up a MATLAB pool or my parallel cluster to run this, because you recall I showed you the parallel for loop. So what we're going to do is define all the files that are in my current directory. So these are all the MATLAB files I would need to run my code. We're going to go ahead and open up a MATLAB pool, which is essentially a cluster of MATLAB workers that I can call and dispatch work to. This one happens to be named Speedy. It's a 16-core machine, and we're going to pass in the file dependencies so it knows which functions to use. Now this cluster happens to be disconnected from my desktop computer here, my laptop, and located in a different area of our campus. So it's actually physically separated from where I'm at, but it's on our local network. And that's one of the reasons why I have to pass to the file dependencies, is to tell it where to grab the files it needs, since these, don't have path to my C drive here on my local machine. So we'll go ahead and open the pool. Now that it's open, we're going to go ahead and run the sweep with defined ranges for the inputs of 1 to 120 for both the leading and lagging indicator. You can say using parallel computing, that took about half a second. And you can see the results here, which show the best results of 3 and 23 as we found earlier. Also plotted is the same surface map indicating which were the two best for us. So this is the main point here, is that I'm showing you a progressive step from going from just playing around at the MATLAB command line to writing a script to encapsulating the work you've done within functions so that you can reuse it multiple times. And that's essentially the state where we're at now. Is now I have a function called parameter sweep, which will operate on any function I put. So I could change this to an RSI indicator, for example, and run this on that as long as I pass it in a range. So now you're seeing how easy it is to build up an algorithm and start to develop more sophisticated systems. So now before I exit this, let me go ahead and close the MATLAB pool. So let's see the speed up I wouldn't have gotten if I didn't use it to calculate the cell. So now it's closed. Let's go ahead and run it again. And you can tell it took about 2.74. So the reason I'm showing this is just showing you how to use parallel computing as you develop an algorithm. And you can see that the speed up is, quite substantial. It's roughly 2.7. So it's roughly about a 5 times speed up. So let's go ahead and open up the MATLAB pool again. So I'll have it available for the next step. So what we're going to do now is clean up the workspace. We're going to start and we're going to load in 1-minute data. So the data I was working with before was daily data. So now let's take a look at something of higher frequency. Let's say you wanted to do intraday trading. So we're going to define things as before, use 80% as my test set and 20% as my validation set. Now what this next section is going to do is essentially going to run a parameter sweep as we've done before. But this time what we're going to do is we're going to use that lead lag function I showed you earlier. And instead we're going to pass in 3 parameter inputs to it this time. We're going to pass in the values for the leading and lagging indicator, as well as some time samples. So what we're going to look at is trading from anywhere from 1 to 5 minutes, 5 to 55 minutes, as well as looking over the hours, 60 to 180 minutes, 240 and 480. Pass that into range as a third argument. So we have our leading and lagging ranges. They're scaling back to the leading lag function, and we'll go ahead and execute this. So once this is done, what we're going to then do is we're going to plot an iso surface. So the result before is I plotted a surface, a 2-dimensional surface showing you the 2 leading and lag indicators as well as the Sharps ratio. In this case we have 3 dimensions, so we're going to basically show volume visualization within MATLAB. So you can see the best leading and lagging indicator that I found was 1 in 100 for roughly 120-minute intervals in this case. And now if we go ahead and plot the iso surface, what we'll see is basically iso surfaces or iso contours within the volume, showing the frequency, fast-moving average, and slow-moving average. So the resolution out here, because the time sample is quite sparse, isn't that high, but what you can see is there's a region of red, which is a high Sharp ratio of greater than 1.2. So anywhere within this region is a trading strategy. So what I could do is I could essentially choose any time frequency I want and find a strategy that will give me a decent trading result. And as we recall from the previous plot, what it had was for one of the indicators it was 1, and for the other it was about 10. So that would be, I think it was this slow one was about 1, the fast one was about 10, so that would be somewhere over here was the maximum that it found. So if you notice that the 100 that it called out happened to be near the boundary of the sweep that I've done. So what I want to do actually here is open up that boundary and sweep a little bit further and see if I can find something better. And then once this finishes, we're then going to run it on the best performer. Okay, so what we can see here is the reported parameters that were found to be the best, which are 10, 394, and a time sampling of 29. Now those are actually shown in this plot. You can see that the best samples, 10, 394, sharp ratio 199, and return of 21.4 or 22.8 in absolute value. So you can see the trading history, the cumulative return, which tended to stay positive, which is pretty good. So this looks to be a decent strategy. Now this again is reported on the validation set where we developed a strategy on. So let's test this against our validation set and see how well we do. You can see in this case we do about a 4.5% return. So this kind of wraps up the first demo, which is to kind of show just how easy it is to develop a simple trading strategy using technical analysis within MATLAB. The next thing I'd like to show you though is how you can quickly turn your exploration in your script into a document of what you've done. So one thing, if you notice that each of these, the double % signs contain bolded characters. Now these are going to be sections of my report when I publish this file. And then the green comments are going to be text. Okay, now before I go ahead and publish this, since it'll take a couple of minutes to run through it again, let me go ahead and open the results of a previously published file. And then let me go ahead and start this, and I'll show you how easy it is to publish results. So what you can see now is it's going back through the script I developed, creating the plots, capturing them. In a few minutes it's going to enter the parameter sweep where we won't see any activity. So at this point, we'll go ahead and open the report. So this is the report published to an HTML format. Now other formats available are directly to PDF, a PowerPoint, or even to Word. So what you can see is that the comments that I had in there are now become sections of my report, or the contents, and I can go ahead and start looking at my report. And what I really care about is let's go ahead and look at the best frequency. So you can find the best one that I found on the trading set, the sharps ratio, the extension of that parameter sweep to find a better set of parameters, which happen to not be bounded any longer by my parameter sweep, as well as the performance on my validation set. And you can see that my report is almost finished. So let's go ahead and give it a few more seconds, and then it's going to reopen the report within this window, which should look the same. Okay, and here's the result. It reopened it in the command window. We can go back to where we were, and you can also browse through this. So the nice thing is that I captured my work, including the code comments. I can document it, all while I'm interactively developing my algorithm. So it helps serve the purpose of self-document, as well as if you have to reuse and share this code, you can give that to other people as well. So let's go ahead and clean up and move on to the second demonstration. Okay, so the next step that we're going to do is we're going to try and extend what we just did using the moving average indicator, and we're going to use a relative strength indicator. So again, we'll go ahead and load in the data. Let's go ahead and take a look at an RSI index, which is also another technical analysis indicator, or in this case it's actually an oscillator, also available within the financial toolbox. So what we're going to do is we're going to run a RunSI index with a window of 14. And then we're also going to run one that takes the closing value and subtracts out a moving average. And let me explain why I'm doing that here in a minute. Let me go ahead and execute this cell. And so what we have here is the two RSI indicators. So a relative strength index oscillates between a value of 0 and 100. And generally the guidance is between 80 and 20 is the range of overbought in this case and oversold in this case. So when you move above the threshold, you'd want to buy. When you move below the threshold, you want to sell. So the green line here is the moving average indicator subtracted from the bund, and the blue line is the standard RSI, not just directly on the data itself. Now one thing that you notice is that the green in general tends to be before the blue, and that's one of the things with an RSI indicator operating on the raw data, is that it can often have have an indicator that's a little late. And the reason we're going to be doing a moving average is to account for that and try and give us a trading signal better for us to react. So this way we're taking into account the oscillations about the mean and not accounting for the changes with the mean as well within the calculation of the relative strength index. So what I've done here is I've captured this command within an RSI command, which is essentially doing the moving average calculation, which is the first parameter. The second parameter is the window on the RSI index. And then I've added, the return calculation using the scaling, accounting for cost, generating the signal, and the threshold. So the threshold is going to be our upper threshold, and the lower threshold is going to be a mirror image of that. So we're going to set 65 just as an example and see how that does. You can see the results here with a moving average of 300, an RSI indicator or window of 20. So the window on the RSI will essentially smooth out the oscillations here. The larger this is, the fewer oscillations you're going to see. The shorter it is, the more oscillations you're going to see. So it's a way of kind of offsetting for the frequency. So you don't want to trade too much based upon noise. And you can see the trading activity and the results in the bottom window. So we developed a simple RSI indicator. Now let's go ahead and do the same thing as we're going to run a parameter sweep as we've done before. So I've run this before, and 55 actually tends to be the best threshold. We're going to run a range of 1 over 300. And again, we'll go ahead and run this. This will take roughly about 20 seconds, 20 to 30 seconds. So what we're doing is the same thing as before. I've defined an RSI function which handles the vectorization of x. This is sent to it from the range. So we're sending in all the parameter values at once, using the par for loop to dispatch the calculation, run on multiple machines, and then return the results through the parameter sweep function. So again, I'm reusing the parameter sweep from the previous example. And then we're going to go ahead and plot the results using the best parameters, given 1 and 2, and parameter 3. Well, parameter 3 will be set at 55 because that's the constant that I'm using in this particular example. So here you can see the results with the trading window, the signals, the return, the RSI index with the lower and upper values. You can see that the best value found for that window is 139, and actually a very short moving average of 4 was found in this case to be optimal. And you can see the Sharpe ratio and the return. So remember the return of around 23.8, because we'll be looking at that later, in a Sharpe ratio of 2.07. So that was done on the test set, so let's just quickly test that on our validation set. And you can see in this case I don't do quite as good as I did in the moving average case using just the RSI indicator alone. If you remember, the previous case was around a 4.5% return. This is 1.5. So let's take the moving average that we've done earlier and combine that now with the RSI. And from the parameter sweep we've done in the previous example, these are the best parameters for it. Now the thing I'm going to do is I'm just going to add these two. So I'm going to add the two signals that I get from the RSI and from the leading lag, add them together and divide by 2. So that's going to still give us a range of -1 to +1. And then we're going to use that to plot the results. So here's the results from a moving average plus an RSI. We get a Sharpe ratio of 2.5 and about a 20% return on our test set, which isn't too bad. So let's go ahead and run that, or excuse me. So the commands that were done here are now encapsulated in this command. So let's go ahead and run that. You can see we get the same thing, but we also get the individual plots. So let me go ahead and show this. So there were 3 plots that were generated. We go ahead and dock them, and then we'll put them side by side. So you can see the 3 plots we have. We have the results from the moving average plus RSI, just the leading and lagging, or the moving average itself, given those parameters, as well as the RSI. So you can see a comparison of the different returns between them. So you can see if I just used the RSI, I would have got a 23% in this case, 19, or 18, and 18.4. So the combination here wasn't optimal, and that's because I didn't necessarily choose the optimal parameters. So you can see in this case that the return we got was less for the validation set. So the thing we want to do now is find the best parameter for that. So what we're going to do is go ahead and run this. And here we do. We have the results. So again, let's go ahead and dock these. So we can compare. And what you have is the RSI result, the moving average, and the moving average plus RSI, which when calibrated tends to actually do better than the other two by themselves, which is a good thing. That's kind of the outcome we were looking for, right? So let me explain at a high level what the evolutionary learning approach is and how it's implemented in my demo. Now, the approach to learning the best trading strategy from different market signals, or you can think of them as states of the market, is implemented as a genetic program, and it is solved using a genetic algorithm. While I'm not going to get into the details about the genetic algorithm or genetic programming, I will give a brief overview of the approach used to identify the best trading strategy. And if you want to know more about the genetic algorithm for solving optimization problems, there's an on-demand webinar titled Genetic Algorithm in Financial Applications that is available from our website. Now, a genetic algorithm is an optimization approach that is based on the principle of evolution. So we start with a parent, for example, this trading strategy shown here. We then breed the parent 1 with another trading strategy, or parent 2, to generate an offspring, or a third trading strategy. Now, this example shows how crossover works, or the transfer of genes from one parent to another in order to reproduce an offspring that has a different characteristics, or in this case, it's a different trading strategy. Notice how the left of parent 1 is retained and the right of parent 2 is retained in the offspring. Notice that the parents 1 and 2 both have 3 signals that are input, and that the offspring only takes 2 signals as input. This is one of the approaches to using genetic programming, is it allows you to select different signals that can be used for your trading strategy. Now, listed below the examples is a binary bit string representation of the trading strategy. Now, the trading strategy is as follows. The first bit is signal 1, and a 1 in this location denotes that I take the signal at face value, or as is. Now, notice here that signal 2 has a 0 in its location. This means that I negate, or not it in logic terms, the signal. So a buy becomes a sell, and a sell becomes a buy. Now, in red are the logic gates, or the connectors that link the strategy signals together. You can see that I have 2 connectors and 3 trading signals. Now, the last 3 bits determine which signal is used, or which ones are active. So, for example, in the offspring, only signal 1 and 2 are active. Or, only signal 1 and 3 are active. Signal 2 is not. So if you look at the parents and the offsprings, you can see how I can build different trading strategies using a bit string representation. And this bit string representation is very easily put into the MATLAB's genetic algorithm routine, which is what I'll be showing you in a few minutes. Now, there's also one more operation that can happen that I would like to explain. That is, a parent can have a random mutation resulting in a change to it. So you can see the OR in the parent 1 is changed to an exclusive OR, or an XOR, in the offspring. Now, this is an example of a random mutation that may occur. Now, if we take a look at the trading rule that I've defined here, what this trading rule says is that I take signal 1, I join it, or AND it, using a binary operation AND, to the NOT of signal 2, and take that result and OR it to signal 3. So we're using Boolean logic here to determine which trading strategy I should use. So if you look at this, what you can see is that I can take a variety of signals, 3 in this case, and I can combine them using AND, OR, or exclusive OR to come up with a variety of different trading strategies. Now, the end result of processing that bit string is that I get a trading signal out of it. It's either a 0 or a 1, depending upon how the Boolean logic operates on the different signals and the connectors that I have. So let's actually return to MATLAB, and I'll show you how this works. Okay, so now let's take a look at the evolutionary learning case. So those first couple cells is load in data. We're going to run the moving average plus RSI. You can see the 3 plots that we've seen before. The result is 26.5. So let's see if we can reproduce that using the genetic algorithm. Now, if you recall, one of the things that we did was that we summed up the 2 indicators to provide us the overall trading indicator and the moving average and RSI indicator. So what we're going to do here is in the genetic algorithm, we're actually going to use the Boolean logic I described on the slide. So the first steps is, we ran the first case to generate the signal, so the signal for the moving average and the RSI indicator. Next thing is, let's take a look at that. Remember I mentioned talking about those signals as kind of states of the market. So These signals, well, I'm using them generated from a technical analysis approach. This could just as well be generated from something else, such as a sentiment analysis, maybe expert opinion, maybe fundamental analysis, or a variety of other sources. But what you can see is we basically have an indicator, a 0 or 1, that's a buy or a sell. And you can see the moving average indicators here and the RSI indicators here. And what we're going to do is we're going to use the genetic algorithm to select the approach for using these. So in the first case, I just sum them together and average them. Let's see if we can reproduce the same results or slightly better using the logic-based approach that I described in the slides. So the first step is we're going to generate an initial population, and what you can see here is those bit strings. So in bit string 1 is the moving average, 2 and 3 are the connectors. So this is describing the logic operation, which can be in this case an AND, an OR, or an exclusive OR. So an AND is a 0, 0 denoted with 2 reds. 2 greens in parallel is not feasible, so you can't find that because that's not defined. A 0 and a 1 is an OR, and a 1, 0 is an exclusive OR. 4 is signal 2, whether it's negated or used as is. And then you can see that everything right now is turned on. So this is indicator 1 and indicator 2, or the moving average and the relative strength index. Both are turned on currently, and when we start to run the genetic algorithm, you'll see that some of these will be turned on and off as we go. So I just want to explain the fitness function really quickly. And what you can see here is the fitness function, which takes in the population, those indicators, the price, scaling, and cost, much like we've done before, calculates the trading signal. It scales it to be between plus or minus 1 when it returns, because the trading signal for the genetic algorithm ranges between 0 and 1. So this will be consistent with the way we've defined a return calculation. And here's the profit and loss, and what we're going to do is we're going to basically minimize the negative of the Sharpe ratio. So we're going to maximize the Sharpe ratio in this case. So we're going to actually do an optimization. So as before, we're going to define our objective function for the optimization routine, or the genetic algorithm routine, as a function handle that takes in only one input, the population, which is what we're going to perturbate within the genetic algorithm. And it's going to use the fitness. So all these others, so the signals, the bun close, annual scaling, and cost, these are all passed in as constant parameters. So this is one way you can pass in parameters that are constant to an optimization routine in MATLAB. I thought I'd just highlight that and show that to you. So go ahead and define the objective. Let's quickly evaluate that on my initial population just to make sure it's working. You can see that I get Sharpe ratios that look reasonable, although they're negative because we're minimizing. And this is the actual setup for the genetic algorithm to go ahead and call. So we have our options, so I'm just setting the display options to iterative. I want to see what's going on at the command window. Population type is a bit string, as we defined earlier. We're sending in what the population size is because we're also giving it the initial population. And then I've defined these custom crossover mutation rules. Basically, we discussed these in the slides, but these are the custom implementations that make sure that we enforce the trading rules or the crossover locations correctly, as well as a plot function that's going to display in real time the optimization routine. So let me go ahead and start that. And what you can see is essentially the same thing we saw before, where you can see the current population and their values. It initially started with what looked to be random or noisy, with a lot of different colors, and very quickly it converged closely to a value. And you can see that most of it's uniform with a few random perturbations here and there, doing an exhaustive search of the area. Doing a continual search of the area. So the output was here. This column is the maximum value. So the genetic algorithm really quickly found the best solution, but then it spent several iterations determining if there wasn't a better one. The best solution found is shown here. So this happens to be, we use signal 1, we AND it with signal 2, which is very much like what we did with the plus operation in the previous example, and both of them are turned on. And the maximum Sharpe ratio is 2.34. Let's go ahead and see how that performs. So this is the results on our test set. You can see that we get a 26.6 or 24.9% return, which is, and a 2.31 Sharpe ratio, which is slightly better than what we had previously. Using the Williams %R oscillator. So as we've done before, we're going to load in data, break it into test set, validation set. The Williams %R calculation is another function that's available in the financial toolbox. We're going to pass in the bun data, as well as an initial estimate of the Williams % parameter of 50. So let's see So let's actually go to the doc, and we can read about what this is. So it's the number of periods. We're sending in the matrix that has the high, low, and the close. And the number of periods is defaulting to 14 if we don't use it. So we'll go ahead and run this and then plot it. You can see the oscillator. Now the oscillator here ranges between 0 and a minus 100. So in general, a trading strategy is that when you cross over minus 50, that's when you would generate a buy or sell signal. So anything above minus 50 is going to be a buy, and that's what's essentially encapsulated in here, is generating that signal. So let's go ahead and look at the results. And you can see the Williams %R with an input of 100 operating on this gives us a sharp ratio. This isn't optimal. We know we can do better. So let's do a parameter swoop to find the best performing parameter for that. And here's the plot of the sharp ratio over the inputs, and we can see that out here around 400 is the best one. Result does say that around a 394 is the one that's chosen, and we get a 23.1. So let's now add the Williams indicator in with the mix of the moving average and relative strength index, and calibrate it using the genetic algorithm as before. So we'll go ahead and generate the trading signals. You can see a similar map as before. This time we've added another one to the mix. Now note that in the development of this demo, I didn't have to change the genetic algorithm. It's generic and scales to the number of indicators that you use, so we can use effectively even more if you want to. But just for purposes, we're going to show it working on 3. This is the initial population. Looks to be fairly random noise, which is good. That means we have good diversity in the initial population to start our search from. The fitness function you can see here is very much the same. No real changes to that. Again, we'll evaluate it to make sure it's working correctly. Looks okay. And we'll go ahead and start it. What you can see is within the first iteration it's found a pretty good result. I don't think we'll improve upon that, but we're just going to spend some time searching the space to make sure we've exhausted any potential indicator that could be better, or combination of indicators that could be better. So you can also see the uniformity of the plot, meaning that we reach convergence rather quickly, or it's narrowing in on a good solution, or the best solution that it's found. And what we have here is the first indicator ANDed with the second indicator, and in this case we're going to OR with the Williams %R, and all of them are active. So it didn't find that one of these are not useful. So it found a solution that's better with all 3 combined than not by itself. And we get the min-sharp ratio. Let's go ahead and plot it. And you can see the results we get here, which is around a 22.3% return on our test set. And let's check that on the validation set, and you can see we actually get about a 3.47 result. Okay, so that concludes the demonstration portion. I'm going to go back to the slides, and then we'll come back and discuss in a little bit about how you can generate C code from MATLAB. Alright, so coming back from the demo, we saw how you can access data from Excel files, develop, backtest, and optimize a trading strategy within MATLAB. I showed you how to generate a simple report from my code. But let's now take a look at some of these capabilities in a little more detail, and the products that are required to do some of the things that I've shown you, as well as the financial products in general. And we'll be discussing those in more detail on the next slide, as well as talking about high-frequency trading, ways you can generate C code from MATLAB, and GPU computing. So let's start with a mapping of the workflow to the most commonly used products in the financial industry. So we have the workflow, which is access, research, and quantify, and share. And the foundation product, of course, is MATLAB. That's the interface from which everything is built. We have add-on products called toolboxes that extend the capabilities of base MATLAB. Now, MATLAB itself is a 4th-generation programming language that has thousands of engineering, science, and math functions built into it. And you can extend them with application-specific areas. Now, an example in the access area is we have a data feed toolbox, a database toolbox, and a spreadsheet link. Some of the core financial products are statistics and optimization, the financial toolbox, which is the foundation for the financial products. I showed a couple of examples of technical analysis tools from that one in the demo. And built on top of that are fixed income, financial derivatives, and the econometrics toolbox. Now under the share category, we have the report generator, which allows you to completely customize the report you can generate, which provides much more flexibility in putting your corporate logo or customizing the look and feel of the report than the simple publish command I showed you in the demo. Now also, there are ways to share your results through an application, which is done using the MATLAB compiler and builder products. And I'll be discussing those in a little more detail as well. And of course, the way to speed up your applications is to use Parallel Computing Toolbox, which allows you to take advantage of parallel computing language constructs as well as any cores you might have on your laptop or desktop. And then there's the MATLAB Distributed Computing Server, which allows you to scale up your computations to a cluster, cloud, or grid. Now, besides being a great data analysis tool, MATLAB is a complete development environment that allows you to develop your own models and algorithms. So listed here are a variety of the great features that are here, some of which I showed. There's a great editor debugger. There are performance tools called the profiler, which can profile your code and tell you where the bottlenecks within the code itself is. Now, there's also a graphical user interface builder called Guide, and this allows you, it's a drag and drop GUI creation tool. Now, MATLAB is also a fourth generation programming language, which also includes full support for object-oriented programming. And another great benefit of the MathWorks environment is that it's multi-platform support, so it runs on most popular operating systems. So let's now talk about deploying your applications with MATLAB. So one approach is to give MATLAB code to others, so this could be your M files. Now, one thing is that sometimes you want to lock down your code so that people can use your code, but maybe you don't want them to modify the algorithm, or maybe there's intellectual property contained within the algorithm. So one of the things you can do to a MATLAB file, or .m file, is to encrypt it. And basically what you get out is a .p file, or a protected file. Now, this is one way you can share your MATLAB code with others without giving away your intellectual property. In addition, you can share your applications by building MATLAB applications. Now, to do this, you need the MATLAB compiler. And what this does is this allows you to build standalone executables, such as the .exe, or shared libraries. Now, if you have a specific target in mind, such as Excel, Java, the web, .NET, or a COM object for Microsoft Windows, or a COM object, there are different products that you'll need to target each of these different platforms. And these are called the builder products. And you can see the names of them listed here. So that's one of the great benefits of our environment, going back to the workflow, is that you can build standalone applications, you can integrate your applications within other systems, or you can deliver libraries to other users you may have that need to leverage your specific trading strategy or algorithm. Now let's kind of change gears a little bit and talk a little bit about high-frequency trading and the MathWorks tools that can help address this space. So the challenges here is that you often have to have latencies that are on the order of less than a millisecond. You need to be able to develop strategies in native code, which can be very time-consuming. This is particularly the case if you're looking to develop strategies that involve FPGAs or GPUs, where you have to write specific code to target a specific device. And of course, hand-translating the strategies that you might develop in, say, MATLAB to the native code can be error-prone and hard to maintain. So what does the MathWorks offer in this area? Well, mainly there are a variety of different things to help you get the performance out of MATLAB or MATLAB code that you need. So parallel computing, which I showed in the demo, is one strategy for speeding up your applications. Now another one is GPU support, or using the GPU, graphics processing unit, on your desktop. Now we'll talk about that a little bit more on the next slide. And then the last one is if performance is really critical, or you need to integrate with hardware or a different software environment, you can automatically generate code from MATLAB, Simulink, and Stateflow. So I'll be talking a little bit more about Simulink and Stateflow in the next few slides. So in MATLAB, the guiding philosophy is the workers extend the MATLAB desktop to work on not just a single resource, but multiple resources. That is the concept behind the parallel computing toolbox. And also contained within the parallel computing toolbox is support for graphics processing units, or GPU. So this allows you to send calculations directly to your graphical processing. So the slide lists some of the basics behind what a GPU is. I'm not going to get into them into a lot of detail. But basically what it is, we're enabling you to take advantage of the GPU cores that are very efficient for solving certain types of problems. Here are the summary of options for targeting a GPU. One is you can just use the GPU array interface within MATLAB and the built-in functions. You can also create custom functions based upon the GPU array and the GPU constructs. And of course, if those aren't enough, you can invoke your own CUDA kernels directly from MATLAB. Alright, now I mentioned another option is to generate C code directly from within MATLAB. And this slide compares and contrasts the approaches of what we call the embedded MATLAB language versus the MATLAB compiler, which I discussed earlier. Now the embedded MATLAB language is really designed around generating portable C source code from MATLAB, and it's really geared towards targeting specific embedded hardware such as DSPs, microprocessors, and so forth. Now embedded MATLAB is a subset of the MATLAB language, and it does include two other toolboxes. Most of the other toolboxes I mentioned earlier do not support embedded MATLAB. Now the thing with embedded MATLAB is that there are no libraries required and there are no limitations on the platform. So what you get is C code generated directly from your MATLAB algorithms. So this can be very important, for example, if you're really concerned about your algorithm performance and want to minimize its memory footprint or have the fastest processing time available, and need to integrate it within your system, which already happens to be using C, C++, or another compatible environment. Now, in contrast, the MATLAB compiler allows you to deploy any software application you develop within MATLAB to the desktop or to the web environments, or you can build callable libraries from within them. So this supports all of the MATLAB language, including the graphics and GUIs, and just about every toolbox. Now, it does require a library to run, which is the MATLAB component runtime, which is a one-time install. Once you have it installed on your machine, you can have many MATLAB applications call that runtime. Now, one of the limitations, of course, is that it's only supported on platforms supported by the MathWorks or by MATLAB. So you can't do hardware-specific applications using the MATLAB compiler. I got a couple more slides and then we'll wrap up. So I mentioned generating C code from MATLAB. Now, another option is to use our other platform product called Simulink. Now, Simulink is a dynamic modeling environment that uses a block diagram approach to defining the model. You can see an example of a trading strategy developed in Simulink shown on this slide. More specifically, let's take a look at the exponential moving average, which is implemented in the block highlighted here. So one of the advantages of using Simulink is it's a visual graphical programming environment that also has hierarchy to it, allowing you to manage and reuse several of your model components across models or a variety of different approaches. And of course, as with MATLAB, there were toolboxes that extended the base functionality. Simulink has block libraries that extend the capabilities, and you can see a couple of them shown here. Now, one of the benefits of using the Simulink platform for algorithmic trading is that you can actually target hardware-specific devices, such as an FPGA. So the added benefit here is that you can also generate C code directly from Simulink. You can even embed MATLAB within a block within Simulink and generate C code from that. And then you can also target FPGAs that are using an HDL language, for example, as well as a variety of other hardware devices. And if you're interested in this, the 2009 Algorithmic Trading webinar, which is available on demand from our website, has some examples if you're interested to get an overview of how Simulink may be used in this approach. So I'll conclude the slide presentation by letting you know where you can find some additional information. Now, an archived version of this webinar will be posted to mathworks.com webinars within a few days. Now, some additional resources we offer can be found on this slide, which is a snapshot of our computational finance application webpage. So to get to this page, go to mathworks.com, click on Solutions, and navigate to computational finance. There's a similar page for financial services industry, and you can also access similar product pages for all other add-on products from this location. Now, another item of interest is that we offer various MATLAB training classes, as well as classes for optimization and statistics, and some of them have been customized for financial applications. So you can find more information about our trading programs at mathworks.com, and they're listed off the Products and Services tab. Now, this slide just lists an example of our upcoming webinars and recorded webinars that may show some applications that are of interest to you. So 2 upcoming webinars we have before the end of the year is Speeding Up MATLAB Applications. This can show you how to write very productive code within MATLAB, or make your MATLAB code as efficient as possible, as well as speed it up using parallel computing, or GPUs. Now, you may also be interested in some of the past webinars that show different capabilities related to the topics that I've shown today. The first one is Genetic Algorithm and Financial Application. This one talks about using genetic algorithm to solve a portfolio optimization problem. And this specific webinar actually goes into a little bit more detail about talking about how the genetic algorithm works using a binary string. So it'll give you more context to what I showed today. And of course, there are other algorithmic trading webinars located on our website that you can access. For example, the 2008 webinar contained a section highlighting co-integration and pairs trading, as well as a little bit of discussion on Simulink. And the 2009 webinar showed some more specific Simulink examples that may be of interest to you. Now, you can also phone us at 508-647-7000 if you're in North America, or email support@mathworks.com with any additional questions you might have about our products or services, or in the case that we don't happen to answer all the questions in the Q&A session today, this could be a good way for you to contact us to make sure that we do answer your questions. Now, if you're outside of North America, go to mathworks.com and click on the Contact Us tab. Now, at this point, I'm going to go silent to address some of the questions that we received over the course of the presentation. Now, I'll try to answer as many as possible, but if for some reason we don't answer your question in some form, please don't hesitate to contact your local MathWorks office or reseller. Now, again, I'll go silent for just a moment, and I'll be back to answer your questions.